Ladies and gentlemen, good morning. My name is Andrea Zanichelli and I'd like to present you a paper titled Influence of Crack Nucleation Location on Fretting Fatigue Crack Path. First of all, I really would like to thank my co-authors from the University of Parma, the University of Calabria and the University of Naples Partenope in Italy. The present paper deals with the simulation of an experimental campaign carried out on a 7050 T7451 aluminium alloy, subjected to constant amplitude fretting fatigue loading by means of an analytical methodology recently proposed by the present authors for fretting fatigue assessment. More precisely, the goal of this research work is to evaluate the influence on the estimated crack path orientation of the location of the crack nucleation point on the contact surface. The main sections of my presentation are here summarized. In particular, after a brief introduction related to the fretting phenomenon, the analytical methodology employed for fretting fatigue assessment is presented. Then, I'll describe the experimental campaign analyzed and the results obtained in terms of crack orientation before some conclusions. Fretting fatigue is a contact phenomenon that occurs when a structural component is clamped against another mechanical part in presence of small oscillatory relative displacements. In such a condition, relative microdisplacements may arise at the contact surface. Two different regimes can be distinguished on the basis of the magnitude of such relative displacements. Gross slip regime, characterized by global relative motion between the components, and partial slip regime, in which the contact surface consists of an inner stick region with no relative displacements and an outer microslip region, where relative microdisplacements of the order of few microns arise. Gross slip regime promotes the wear of the material, whereas in partial slip regime, the main damage phenomenon is the nucleation of cracks at the contact surface due to high stress gradients. Most failures due to fretting fatigue occur in high cycle fatigue regime conditions and are characterized by high stress gradients and multi-axial stress state. In order to analyze fretting fatigue problems, the stress state within the structural components needs to be determined firstly. To this aim, either analytical formulations or numerical models can be employed. Then the fatigue assessment follows. Considering the fact that in the case of fretting fatigue elastic partial slip loading conditions, the crack nucleation phase generally involves around 90% of the total fatigue life, crack nucleation models can be applied in order to assess the fatigue behavior of fretting affected components. Finally, due to the high stress gradient in the vicinity of the contact zone, it seems more appropriate to analyze suitable quantities summarizing the stress field related to a process zone instead of examining the fatigue load history related to a single point. Moreover, it is important that the fatigue assessment is performed in a point located at a certain distance from the contact surface. Therefore, a local approach should be employed in conjunction with the above fatigue criteria. An analytical methodology recently proposed by the present authors is here employed to perform the fretting fatigue assessment of metallic structural components. In particular, such a methodology allows to evaluate both the crack initiation direction and the fatigue life of metallic structures under fretting fatigue elastic partial slip loading conditions in high cycle fatigue. The main steps of the proposed methodology are here summarized. The first step consists in the definition of the input data. Then the stress state in the vicinity of the contact zone is computed within the specimen by employing analytical solutions related to cylinder to flat or sphere to flat contact situations. Next, the hotspot is located on the contact surface, and after that, the orientation of the critical plane is determined by means of the joint application of the multi-axial fatigue criterion proposed by Carpinteri et al. And the critical direction method proposed by Araujo et al. Finally, the fretting fatigue assessment of the component analyzed is performed at the verification point by employing the Carpinteri criterion. First of all, three categories of input data need to be set, that is, the geometric sizes, the material properties, and the loading conditions. Then, the second step deals with the determination of the stress state within the specimen. To this aim, let us consider a typical fretting fatigue configuration where two fretting pads, either spherical or cylindrical, are pushed against a flat specimen in partial slip regime as shown in the figure on the left. A constant normal load P and a cyclic tangential load Q are applied to the pads, whereas the specimen may experience an axial stress named bulk stress sigma B. This system is characterized by a plane strain condition and may be consequently considered as a bidimensional problem. The width of the contact area is obtained by means of the Hertzian theory as well as the contact pressure distribution between the specimen and the pads that is represented in blue in the figure on the right. Moreover, the solution proposed by Catano and Mindlid, modified in the way suggested by Nowell and Hills, is employed in order to evaluate the width of the inner stick zone and the contact shear distribution that is qualitatively shown in red in the figure on the right. Then, the stress tensor in the vicinity of the contact zone can be computed by superimposing the stress contributions due to the constant normal load, the cyclic tangential load, and the bulk stress. Once the stress field is evaluated, the hotspot H is looked for on the contact surface by means of the equation reported here. In particular, the hotspot is assumed to be the point where the maximum value of the average maximum principal stress is attained. Note that, for the examined configuration, such a point is found to be at the contact trailing edge, as is shown in the figure on the right. This is in general in agreement with the fact that the main cracks are expected to nucleate in correspondence to the stress concentration region that is the edge of the contact. However, experimental evidences of cracks starting within the contact zone close to the edge are available in the literature, and therefore a parametric study on the crack nucleation location starting from the contact edge and moving inside the contact surface is performed in the present study in order to evaluate its influence on the crack path orientation. The next step consists in the determination of the critical plane orientation by exploiting the critical direction method in conjunction with the Carpinteri criterion. In more detail, material planes with different orientations are examined. Then, a suitable fatigue parameter is computed for each of such material planes, and according to the present methodology, the equivalent stress amplitude and equivalent A, defined according to the Carpinteri criterion, is taken as such a fatigue parameter. Note that in the bidimensional representation shown in the figure on the right, the considered material plane coincides with a segment starting from the hotspot H and having length equal to twice d. Such a length d is assumed to be equal to the average material grain size in order to take into account the material microstructure following the philosophy of the theory of the critical distance by Taylor. Finally, the number of loading cycles to failure NF-cal is obtained according to the Carpinteri criterion by solving the equation reported at the top of the present slide by means of an iterative procedure. It is important to highlight that the values of the stress components are computed at the critical point P critical and are referred to the critical plane. Note that such values are calculated by considering the critical plane orientation being fixed and equal to theta critical. Moreover, the point where to perform the fretting fatigue assessment is assumed to be located at the end of the segment, with length equal to twice d and direction defined by the angle theta critical, starting from the point on the material surface assumed to be the crack nucleation location. Now let me go on to the experimental campaign available in the literature and here analyzed. Experimental tests in partial slip regime were carried out at the University of Brasilia. More precisely, flat dog bone specimens and cylindrical pads, both made of 7050 T7451 aluminum alloy, were used in order to carry out the fretting tests. Both mechanical and fatigue properties of the material are listed in the table shown here, and moreover the average size of the small grains was measured equal to 8 microns. In the present slide, the fretting loading conditions are summarized for each test. The bulk load, when present, were applied firstly in order to avoid the offset of the slip zones. Secondly, the normal load P was applied, and finally the cyclic tangential load was added with a frequency equal to 10 Hz. 19 specimens were tested, and the tests were stopped at 10 to 6 loading cycles in order to analyze the experimental crack path. In the present slide, the maximum and the minimum values of the crack path orientation observed during the experimental campaign are plotted for each loading configuration. The experimental crack path orientations were inward the contact region with values ranging from 7 to 55 degrees. Moreover, the crack path orientation estimated by means of the analytical methodology previously described are added for comparison. Note that such values are computed by considering the crack nucleation location in correspondence of the contact edge. The estimations were inward the contact region in accordance to the experimental observations, but with lower values ranging between 4 and 7 degrees. It is important to highlight that the experimental values were measured at a depth equal to 56.5 microns, whereas the theoretical ones are related to a length equal to twice the average grain size of the material, that is 16 microns. Different cracks starting with the contact zone, close to the contact edge, have been observed in the experimental campaign analysis, as you can see from the picture of a specimen type number 2 reported here. Therefore, a parametric study on the crack nucleation location, starting from the contact edge and moving inside the contact surface, is performed in the present study in order to evaluate its influence on the crack path orientation. More in detail, in addition to the crack path orientations estimated in correspondence of the contact edge shown in the previous slide, other 3 different points are considered for crack nucleation location. Moving inside the contact surface, such points are point B, that is the point characterized by the maximum value of the width parameter on the contact surface, where such a parameter is computed by multiplying the stress component acting parallel to the contact surface, sigma x, by the shear stress, tau, and the relative slip, delta. Point C, located in the middle of the slip zone, and point D, located between the slip zone and the stick zone. The values of crack orientation estimated in correspondence of the 4 different locations previously described are listed in the present slide together with the experimental ones for each specimen type. It can be noted that all the estimations are inward the contact region. Moreover, as the crack nucleation location moves inward the contact region, that is from point A to point D, the estimated values of crack orientation increase. Therefore, it seems that a crack nucleation location within the contact zone allows to better estimate the crack orientation. In the present slide, the crack path orientations estimated in correspondence of point B are compared to the maximum and the minimum values of the crack path orientation observed during the experimental campaign for each loading configuration. It is important to highlight that point B, obtained by maximizing the width parameter, seems to be a good candidate for crack nucleation location. In fact, better estimations in terms of crack orientation are obtained by means of the methodology employed in the present paper when point B is considered instead of point A. Moreover, the location of point B seems to better reproduce the actual crack nucleation location observed in the experimental tests. And now let us move to the conclusions. In the present paper, the crack path orientation of a 7050 T7451 aluminium alloy subjected to constant amplitude fretting fatigue loading has been investigated by means of an analytical methodology based on the joint application of the multi-axial fatigue criterion proposed by Carpinteri et al. And the critical direction method proposed by Araujo et al. An experimental campaign available in the literature has been considered, and the crack of the orientation has been determined in correspondence of different locations starting from the contact edge and moving inside the contact surface. The crack orientations estimated by considering the contact edge as the crack nucleation point were inward the contact region in accordance to the experimental observations, but with lower values. Moreover, it has been found that as the crack nucleation location moves inward the contact region, the estimated values of crack orientation increase. Therefore, it seems that a crack nucleation location within the contact zone allows to better estimate the crack orientation. In particular, the point on the contact surface which maximizes the width parameter seems to be a good candidate for the crack nucleation location. Thank you for your kind attention.